In this video, I'm going to work through an example of a multivariate analysis technique called principal component analysis. The data that we're going to look at is a data set on 48 turtles, and the measurements are the length, the width, and the height of the turtles measured in millimeters. And then we've also recorded the sex of the turtles as well, although we're not going to use the sex directly in the analysis. So, for example, here's the first 6 turtles. They're all female, and the lengths and widths and heights are all as shown. So, principal component analysis is a method for representing the variability in a data set in a more simplified way than the original data. So what I mean is, if we think of the variables, so in this case length and width and height, as representing dimensions, then this data set we can think of as having 3 dimensions. I'm just going to ignore sex for now. So thinking of this as a 3-dimensional data set, it can be challenging to consider data in a high number of dimensions. Data in 3 dimensions, I guess it is possible to consider that there are such things as 3-dimensional scatter plots that we can use to look at data like this, but it is a little bit challenging to do that. And you can imagine examples larger than this where we've got many more than 3 variables, and so we've got very high dimensional data. And so principal component analysis is what's known as a dimension reduction method, where we're hoping to summarize the variation in the data using a smaller number of constructed variables, and these constructed variables are based on the original variables, usually in the form of linear combinations of the original variables. And the hope is that most of the variability in the data can be explained using a small number of these constructed variables. And so in that way we can reduce the dimension of the data set so that we can understand it and analyze it and visualize it more easily. So that's the idea. The first step in the principal component analysis is usually to scale the data so that all the variables have a mean of 1 and a standard deviation of 0. That's not always the case, but it's typically the first step, and that's what we're going to do here. So I'm just going to skip ahead to where we do that. So one way is to do this by hand. It's much easier to simply use the scale function here. So if I apply the scale function to the turtles data, and I'm not going to worry about the first column. That's why I've got -1 in here. It wouldn't make sense to scale that anyway because it's a categorical variable. But now if I look at the mean and the standard deviation of each of the variables, we can see the standard deviations are all exactly equal to 1, and the means within rounding error are all equal to 0. Okay, so once we've done that, then we could take a quick look at the data. So for example, here's the height plotted against the width. So I'm just looking at 2 of the variables here, and I've colored the points according to the sex of the turtles. So the female turtles tend to have a larger height and a larger width than the male ones, interestingly. And you can see the nature of the scaling here, mean of 0 and standard deviation of 1. So we could look at all the combinations of the variables using scatter plots. But that's not what I want to get stuck on here. Instead, what I want to do is I want to skip ahead and do the principal components analysis. So that's down here. Here we go. So there's lots of different functions in R to do principal components analysis. The one that I'm going to use here is the prin comp function. So as usual, if we want to know more about that function, we can type it in here, and that tells us all we need to know. Okay, so I'll just apply that function to my scaled data, and then I can summarize some of the results using the summary function. So one thing we can see is what happens is the analysis creates principal components. So it starts with the first one, component 1, which explains as much of the variability in the data as it can. And then the second one explains as much of the unexplained variability as it can. So whatever has not been explained already by component 1. And then component 3 tries to explain as much of the variation that's left over that hasn't been accounted for already by components 1 and 2. And so this proportion of variance here is a measure of how much variability can be explained by each component in turn. So the first component here is explaining 97.9% of the variability, which is huge. You don't often see such a result like this for the first component to explain so much of the variation. The second one, there's not much left to explain, but it explains another 1.4% of the variability. If I add this number and this number, I'm going to get a cumulative proportion explained of 99.3%, so I'm pretty much done by the time I've got component 2. Component 3 will take us all the way to 100%. I can present that information in what's called a scree plot. So there's 2 steps to doing that, and here's a scree plot. So this is there's different ways of drawing a scree plot. Sometimes you can use a line plot. In this case, it creates a bar plot, and we've got percentage of explained variance on the vertical axis, and then each dimension in turn on the horizontal axis. And so this just graphically shows that almost all the variability, almost all of the variance is explained by the first component or the first dimension. Next thing we're going to look at are the loadings for the first principal component. So we can do that using this code here, the word loadings, and this number 1 here is so that we can just focus on the first principal component. If I left that off, I would get all 3. But I just want to focus on the first one because that's all I really need to focus on, because this scree plot is so extreme that almost all the variability is explained by the first component. I don't really need to worry about the other 2 components. So the loadings here, you could think of this as weights on the different variables. And here I've pretty much got the same weight on each variable. It's about 0.58 for each one. And so what this tells me is that first component is, we can think of it as a measure of overall size. And that's pretty common with biometric data like this, that the first component is measuring the overall size of the particular organism that we're looking at. And so this is an example where we started off with 3 dimensions, but we can explain most of the variation between the different turtles just with 1 dimension. this first principal component that we can think of as the overall size of the turtle. Next, we can calculate the scores on the first principal component. So if we do this calculation here, and then we can print out the scores. So if we think of that first principal component as a measure of the size, the overall size of the turtle, the scores tell us where on that dimension each individual turtle lies. So the first one has a value of minus 1.98, so it's negative, it's relatively large magnitude. So this first turtle is a smaller turtle, and this next one's a little bit bigger, but also kind of on the small size. It's not till we get to, let's find one that's kind of on the big side. Maybe this one, turtle number 8 is a little larger. Turtle number 9's larger still. Turtle number 9 and number 10 are about the same size. Okay, and so on. So that's there's some really big turtles here though. This one's pretty big. This one scores 4.56. Is that the biggest one? Yeah, I think that's the biggest turtle in the whole sample. Turtle number 21, 22, 23, 24. Turtle number 24. So we could confirm that if we look at the data again. So let me just go back to the top to see what syntax I need to look at the turtle. Well, I just called it turtles, didn't I? Okay, so what did we say was the big one? Turtle number 24. So yeah, we can see that's a big turtle. It's got a length of 177 millimeters, a width of 132, and a height of 67 millimeters. That's one big turtle. One big turtle. And what did we say was one of the smaller ones? Let's go back to our scores. Where's a big negative number? Is that the biggest negative number? Oh, it'll do. That's turtle number 25. Okay, so let's look at turtle number 25. Is that right? Yeah, it's the one right after the really big one. So turtle number 24 is really big. Turtle number 25 is really small. It's only 93 millimeters long and 74 millimeters wide and 37 millimeters tall. So if you just compare these two turtles, we've got one really, really big one, a female, and then one really, really small one, a male. Okay, so let's see. Let's do one last thing. If I can find my way back to the code. There's a lot of code in this script file. Okay, here we go. Here's the turtles again. Okay, so let's look at a graph, a biplot of the first two dimensions showing both variables and observations. Okay, so let me zoom into that because it's a little hard to see. Okay, so what this graph is showing us is it's got the first principal component on the horizontal axis and the second principal component on the vertical axis, and it tells us what proportion of the variation can be explained by each component. So 97.9% for the first component, 1.4% for the second component, and so that's why this graph is kind of stretched out in this direction, is because this dimension, the first dimension, is much more important than the second dimension. So we really want to focus on the first dimension and not worry too much about the second dimension. And then we've got the turtles marked according to color. The red ones are females and the blue ones are males. They've got different symbols too. The females are circles and the males are triangles. And the mean for each group has a bigger symbol. So this large red circle is where the mean of the females it lies for on dimension 1 and dimension 2, and then similarly for the big blue triangle there for the males. And then so we can see if we describe this first dimension as representing size, so the larger turtles are going to be on the right and the smaller turtles are going to be on the left. The females tend to be larger than the males. I mean, there are some smaller females for sure, these ones here. There's not really any really big males. This is the biggest male, this one. And then the other thing that this graph shows are the three original variables, so width, length, and height. And so these arrows, the length of the arrows and the angle that they're pointing at, give us information on how these variables are represented in the two different dimensions. So if we think about the first dimension is in the horizontal direction, so all three variables are kind of equally weighted in terms of the first dimension because they've all got a similar length in the horizontal direction, and the angles at which they're pointing, they're all kind of pointing towards the right. And so that's telling us that this first dimension is an overall size measurement. The second dimension, I'm not even going to try and analyze that because it's only representing 1.4% of the variation. It's not worth trying to analyze. So okay, so that's one graph that we can look at. We can also look at what's known as a correlation circle. So what this does is it reproduces those arrows with the original variables printed on them, but now let's just zoom into this one too. The plot isn't stretched out according to the values of the proportion of variation explained. Instead, it's just more like a square plot, so it can be sometimes a little bit easier to understand how the original variables factor into the dimensions using this correlation circle. But it's telling us the same story. The first dimension is weighting equally on each of the three variables. So that's an example of a principal components analysis on a data set where things are fairly straightforward. We only had three variables originally, and applying the principal components analysis, we reduced the dimension from 3 to essentially 1. One dimension can explain the variation in that data pretty well. In the next video, we'll look at a slightly more complicated example where we've got more variables and we're unable to reduce the dimension all the way down to 1. So the dimension reduction isn't as successful as it was in the turtles example, but it is still a worthwhile analysis because it does simplify the patterns in the data.